No, 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 no. Why is it doing it? Did anyone do this? Or just by itself? Maybe it reacts to my mouse. I don't know. So I put a few things together, which the only really numerical part is actually letting you try cloudy. Right? And I thought it would be useful exercise because it is a good code. It is a code that can be used for many different applications. And in cosmology and galactic studies, it's been used extensively. Right? And so it's a useful skill, basically, to know how it works and what you can do with it. So you can run Cloudy as an application, right? But of course, then you only can do whatever it allows you to do. But in fact, the Cloudy should be treated as a library. Right? It's a library of tools to study physics, radiative physics of gases. So what I have on the website, let's see. I need to connect. So I presume you already installed it, because if you don't install it, it will take a while to compile. It's a rather large code. So what I have here is this turbo, which I cannot move higher. So this turbo, I will show you what it contains. I get my server to run. This turbo contains this folder called chfun. So if you download it and you have cloud installation, you need to untar it inside your Cloudy directory, which should be this, because we use Cloudy 10. So if you have Cloudy installed, you untar it so that this directory appears right there. So then, let's see, I probably can make a font larger. Right? So then if you go there, what you'll see is this main program, and then you see this small utility that basically drives Cloudy. So you can look at it, or you can use it as a black box. So it's something that I wrote, right? And I try to put some comments also. You know, astronomers are kind of not very fond of putting comments in codes. So it's really one function that allows you to specify total hydrogen number density. So it's not a barrel number density, it's a hydrogen number density of all hydrogen nuclei, total proton density. Temperature in Kelvin and metallicity in solar units. So the nuclear metallicity would be 1. Also, whenever I say metallicity in solar units, I don't mean the metallicity of the sun. I don't care what the metallicity of one star in the middle of the galaxy is. What I mean is the metallicity of gas around us, right? It's the metallicity of the solar neighborhood. And then there's a string that lets you tell Cloudy which radiation field you want to use. Then in the output, you get a cooling value of the cooling function and the heating function. Also, you can get much more from it, but we're talking about this. And then you can just let it write some information to some file if you want. So this file is, again, you can either use it as a black box, or you can try to understand what it does. There are a few commands you need to use, like initialize the Cloudy, then read into it the values of those parameters, density, temperature, metals. You specify abundances of heavy elements. For cooling functions, not all the heavy elements are important. Those you can ignore. And then it lets you put this numerical parameters, it tells you how you converge. Again, I don't want to go into detail about what those are. So the Cloudy actually computes the radiative transfer problem for a slab. So as a radiative transfer problem, it's completely useless because it assumes the slab doesn't have any velocity in it. So it's a homogeneous static slab, which only happened in like in this room, but it don't occur outside the Earth. So as a radiative transfer process, it's not very useful unless you modify it so it actually can account for the velocity distribution. We'll talk about this velocity distribution later. So what I'm doing here, I'm actually making it optically thin by specifying the width of the slab as 1 centimeter. And I don't think any gas anywhere in the universe, if it's 1 centimeter thick, will absorb anything. So I have to switch off hydrogen molecules, CO, I switch off dust. There is no Compton effect here. There is, I forgot what scattering capacity is. That's because in order to do molecules, you really have to do radiative transfer. Molecules are completely useless without radiative transfer. So if you're not doing a full radiative transfer, you better don't use them at all because you just get them wrong. And then all this thing does is just runs cloudy this CD drive, and then you get a few numbers out of it at the end. So this is, again, you can just use it as a black box because it lets you compute the cooling function, right, so, and heating function together. And then the main routine it just runs this. So this one is really unsophisticated, but you can modify it. It's so unsophisticated, it should be straightforward to modify it, even if you don't have much programming experience or never used C++. Well, C++ here is relevant, it's written as plain C. Even if you never use C, you can probably modify this. So all it does is specifies radiation field. I let you choose 2 of them. So this is a C comment. So if you want to use this rather than that, just move these 2 lines here. So right now it uses ISM radiation field with a factor which is set to 1. So just use the radiation field as it is in the solar neighborhood, but you can easily change it by some factor to make it larger or smaller. And then you use solar metallicity and number density of 1 particle per cubic centimeter, 1 hydrogen atom. And then all it does is for 8 values of temperature from 10 to 10 to the 8 in steps of 1, right? It runs this function and prints the cooling and heating functions, and the output of that should be this. At least when I run, that's what I get. So you get this heating and cooling function, and again the units are ergs times centimeter cube per second. Right? So that when multiplied by density squared, you'll get the rate of change of energy density. So I didn't have a very detailed plan of what you can do with this, but I thought what would be useful is to just play with this as a black box and then change radiation field and change densities and metallicities and compute this cooling function for a few values. And presumably you all have Python, so you can plot or some plotting software, so we can actually draw a cooling function and then simply see how it changes, right? Both cooling and heating functions. You can also find places where heating is equal to cooling, right? In which cases will be somewhere between these 2 points, and those will be the thermal equilibrium, right, for this gas, for example. That's actually all. So I'm not going to give you many more instructions. So there are, again, what I actually said already here. So you can, it's hands-on, so you're supposed to try whatever you like. So if you have questions, we can discuss that here. But for now, I will just let you play with that. And again, one of the lessons I would like you to take from that Cloudy is very slow. You see it takes non-trivial amount of time to compute these cooling functions with a few values. So if you think about using it as a way to compute your cooling functions in the simulation on a 1,000 cube grid or 1,000 cube particles, every time step, forget about that. Even if you have 100,000 cores, it will be way too slow. So in addition, so this is something that is probably most useful. Right? If you don't like that, there is, first of all, an analytical problem which I formulated here, which builds on my discussion of IgM, except that I forgot that Hubble expansion in this term. So the equation is actually not right. But you can still play it as it is. It's not very useful, though. And then there is a third project that only requires from you plotting things. So this is going a little bit ahead. On Saturday, I'll talk about star formation stellar feedback and how different modes, of stellar feedback sort of relate to each other. So supernova, radiation pressure, etc. So this allows you to plot time dependence, let's say supernova feedback, winds, barometric luminosity, ionizing luminosity, etc., as a function of time. And in part, it will be an attempt to reproduce the plot I will show you on Saturday. But I also left a couple of questions here for you to think about that, and basically compare what radiation feedback from stars, how radiation feedback from stars compares to, say, supernova feedback. And then you can also think about what it means for escape fractions. So this only requires plotting, and these instructions to tell you which combs from those files you should plot against what. Another thing you can do, guys, is to, if you notice here, right, so this heating function is higher than the cooling function at 1000 Kelvin. So if you take this gas at 1000 Kelvin, it will heating wins over cooling. At 10,000, the cooling function is larger than the heating, so it will actually cool at 10,000. So if you add more points in between, you'll find a place where those are equal, and that will be the thermal balance, right? So if you just let the ISM gas sit, it will get to this temperature. So then you can check how it actually changes with metallicity. If you now decrease the metallicity to low values, like high redshift galaxies, would the ISM be hotter or cooler than, say, in the Milky Way? So should I do something?
Sorry?
Should I do something else?
Well,
I didn't see what Walker was doing.
sorry?
I didn't see what Walker was doing, so I'm not sure what.
Okay. In fact,
One of the things we show is that
he let some time
this is pressure, which is the
for the student to try themselves, and then he showed exactly what he
these three
expected
curves have all
for
the
them.
same parameters. And
So maybe, well, if you have, for example, if you have a tool to plot the Gnedin function, you can just show
Well,
each
I
shape.
don't use Python.
No, you don't have a.
But I showed Gnedin functions. Yeah. Guys, for example, see what I've done right now. I was just curious myself, and I think I actually learned something that I didn't know before. So I plotted here the ratio of heating to cooling to heating function as a function of metallicity for solar 0.3 and 0.1. Right? And remember I said, the photonized gas is always at 10 to the 4 degrees. But actually in the Milky Way, right, at 1, if you look where this crosses 1, cooling equal heating, it's like 4,000 Kelvin. So I actually haven't appreciated myself that ISM of the Milky Way is that cool, right? And that's just the way, where the thermal equilibrium is in this gas. Okay? which is a property of cooling and heating functions. If you go to lower metallicity, then you very quickly go to about 10 to the 4. So for 0.3, which will be somewhere between LMC and SMC, so for 8,000, it's heating winds. For 10,000, cooling winds. So it's somewhere around 9,000. If you go to 0.1, which is just a little bit lower than SMC, then it's somewhere around 11 or 12,000. This thing. Yeah.
So for the first spectral model, this factor parameter is not an intensity, it's a redshift, right?
For the first, yeah, it's
Yeah.
actually.
Yeah. Okay.
No, that's actually the amplitude. The redshift is a separate keyword.
Yeah, but it's not possible to make factor more than 10 because the redshift couldn't be more than 10.
Wow, and the documentation says it's actually a factor. It's
For HM
Oh, 5.
5?
Yes, that's what he. 1,000 it works.
It works
For 1,000.
factor more than 10.
Oh, put 1,000 right now, yeah.
So for the first model. So for me,
Yes.
it's strange.
What does it say?
Let's see. Somewhere here. So. Okay.
No, you didn't run.
Yeah. Redshift requested. Understand what it's saying. So the first parameter is the
and
redshift.
just put the redshift. Put the redshift there too.
So yeah, because this model has two parameters, one redshift and yeah. So
No, just put here, right, redshift 3 and then
okay. Yeah.
li-
So that's
leave
right.
the factor.
So it reads this one as
No,
redshift. Yeah.
just
with
write,
the
just
double-
write
Mhm.
redshift 3. That's then it's a bug in Cloud.
Yeah.
You know.
So it should work now. It should work now. Yeah. So it's now once again.
Well, it's a bug then because it shouldn't be doing that.
Nick, I missed your point on the CO and the H2 molecules. So why do you disable them?
Because you need to do radius transfer. It's not
And you can enable it
Hmm?
in you can enable it in.
Well,
in
you
Cloud.
can,
But then you need.
the one you won't be doing the right physical model
Okay.
because then you'll be doing homogeneous labs. That's kind of silly.
Yeah. Okay. But it's possible to enable.
Yeah.
Okay.
So if you ask me about molecular mechanisms, so the reason why they put here. Because you need to do true radius transfer to do molecular correctly. Because we'll talk about how it destroys tomorrow. So you need to actually do radius transfer in lines, which is a heck of a exercise. So you can do that by increasing this Tmax to some reasonable number and setting the Coulomb density. But the problem is that then Cloud assumes that you have a homogeneous slab of gas which have no velocity dispersion in it. And just it never happens in reality. Right? So those things don't exist. And so the physical model that it has inside it for doing radius transfer is actually very unphysical. That's why. The first reason I disabled is because I wanted to get optically thin cooling functions. So in principle, you can enable those, right, or enable all other things. But the way Claudia does it, that doesn't actually make much sense.
Does Cloudy take into account the cooling due to hyperfine transition of carbon, for example?
Yeah, well, that's what dominates the low temperature, right? It's carbon 2.
Yeah, yeah, exactly. But so it's implicit. You don't have to switch it on or off.
I don't think you can switch it off unless you assign the carbon abundance to 0.
Okay, no, that's what.
It doesn't.
So it's really taken into account.
Carbon 2 is the main coolant in low density.
Yeah, exactly,
Yeah.
exactly. So it's on. Okay.
Yeah,
in
you
fact,
know,
in fact, we
you
see
can
it.
only switch it off by that.
Yeah,
You
I
actually
see.
see it because the cooling functions. Oh, this cooling. This is C2. There's nothing else here.
Yeah, yeah. No,
Well,
indeed, so-
there are others, also iron and oxygen, but it's
No, I
a little
expected
bit.
that you could switch on or off different type of cooling, for example, cooling due to collisions or what. No.
You can switch off some things. I don't know if you can switch individual levels.
Okay.
You can go into the code and hack it.
Yeah, sure.
But then you need to know which level. I mean, it's.
But
I
anyway,
hacked it.
it's very
Yeah.
interesting. I think the driving routine is extremely simple and it's,
Yeah, it's
you can it's very useful, I think.
well, that's why I wanted to
Yeah,
give it
good.
because it's maybe useful in the future. So is there anything else you would like to talk about? No, ask any questions? Want me to do something? Because we are getting close to the end. Right? I don't know how many of you actually tried that, but so this is driver for the Cloudy. Just keep it somewhere because one day you might want to do something with this, and then actually going into Cloudy documentation and figuring out how to do things. That's a big achievement by itself. So if someone can tell you how to use it, it's not very well documented, unfortunately. It's still better documented than most of our codes, but still. So is there anything that you would like to discuss?
Well, I think if it's not the case, we can close the session. Thank you, Nick.
No? Thank you.
And tonight we won't have dinner at the -1 level, but at the -2 level. There is a